Hello, Pre-Calc Honors kids. This is Mrs. Orloff again, and we are going to get through our last day of parametrics. So we will be wrapping up this unit, and I will be placing an announcement soon about your test on 6163. So we're going to continue with some linear type of parametrics, and then we'll move on to some other things. So we're going to deal with Superman and Lois Lane. So I'd like for you to take some time and pause this video, read through this, and I'd like you to make the table of values. You're going to determine if Superman is able to save Lois. So I've underlined some key information that you would need to pay attention to. Essentially, Lois' average rate of change is 65 miles per hour. Superman's leaving 3 hours after her. He finds out that once he leaves, the bomb's going to go off in 2 hours, and he flies at a velocity of 155 miles per hour. And we want to know if he can save her. And we can see by a table of values that, unfortunately, he is just not going to get there in time. So the answer is no. He doesn't save her. But the original Superman, just so you know, the original movie, you guys weren't even born yet, he flies in the opposite direction of the motion of the Earth and turns time backward to save her life. Just a fun fact. But no, he doesn't save her. And so a couple things we can do here. We want to do a simulation on our calculator of the situation, but I also want to talk about how we would do this algebraically. Before we continue, I want you to take a moment to figure out how fast would Superman have to fly to save Lois at the last moment. So again, these are things that can come up on your test. So you should really pause the video and take a moment to think about it. So at 5 hours, Lois is 325 miles away, and Superman only has 2 hours to get to her. So we can see that we just do 325 divided by 2, and this is the very speed that he would need to fly in order to get there. So we need to now write equations that model the situation. We want to model Lois's situation using parametrics, and then Superman's situation modeling parametrics. So we need to think about the horizontal distance and the vertical distance. Now, the vertical distance isn't going to come in play because we're thinking about this as horizontal movement. Okay, so we know that Lois, we have distance equals rate times time. So her horizontal motion is simply c5t. And we have to think a little bit extra for Superman because we do know his velocity is 155 miles per hour, but he starts after Lois. So if I use t as the time that Lois is traveling, I have to think about Superman as t minus 3. Now, since we're thinking about this as horizontal motion, I'm doing a simulator. So though the vertical distance doesn't matter, I really want to have the opportunity to see this on my graphing calculator. So my goal is to really pick different y values for Lois and Superman. So I just say, well, Lois was a pretty tall chick. So we're going to say, all right, 6 is her height in feet. Now, you could pick a different number. It would totally be fine. It does not affect the result of the simulator. And I'm going to say that Superman's going to fly about 100 feet off the ground. So his height as he's flying. And now you hear my dog Ginger drinking water in the background. As always, I always have my co-teacher Ginger, my blonde lab mix, and Izzy, my bug, my half pug, half Boston Terrier with me. So now that I've given you the equations, I would like for you to create this into your calculator, and I want you to think about the window. And I just kind of want to get you get that. And then we're going to talk about, what about a finish line? What if we create a finish line and we can visually see that? Pause the video, figure out your window. You can see how I chosen to create my window. We know we need to go beyond that 5-hour mark. My step is every 1/10 of an hour. And you can follow along with my Y max or min. Now, your window may fluctuate a little bit, and that's fine. Right now, we want to create a finish line. We know that at 5 hours after looking at the table, she's 325 miles away. So the Y, we're trying to create that vertical, we're creating a vertical line, and a vertical line that will start at x equals 325 miles away. And there's many ways you could do it. I'm just going to say, that's a mess, 60 t. And I think about that. When t is 0, I have 0. When t is 1, it's already at 60 feet, right? We need it to get to 100 feet where I've chosen to place Superman. So if you haven't already gotten your Lois and Superman in your calculator, do so. And then also place your finish line. Make sure your mode has this graphing in a simultaneous mode. Okay, so you can see my graphing calculator set up, pink for Lois, blue for Superman, black for the wall. My window, as stated, I did change my Y max to 120. I didn't really need that 200, but that's your choice. I'm going to hit graph, and as soon as I see graph, I'm going to witness the whole situation unfold in front of me. So we see Lois taking off. You see the wall being built out there, which is the finish line, this black line here. And Lois is going, and you'll see Superman start 2 hours into it. And this is moving kind of slow, but I want it. And here comes Superman. He's trying to catch her. And she's about at the finish line, and you see that it doesn't work out so well for her. So now that we did a calculator simulation, what if you didn't have a calculator? Again, in this situation, you could probably make that table pretty quickly. But since I'm only dealing with this horizontal motion, all I'd have to do to figure out at what time Superman would have caught up with her given the scenario, I would just have to set these things equal to each other, and I would have to solve. And I would solve that it would be slightly over 5 hours. So now that I've done horizontal motion, I'd like to do some vertical motion. And then I'll get into one of the more popular, a baseball type problem. So I'm going to run pretty quickly through this. I have a flare that's shot straight up. So we have that projectile from a bridge, 75 feet. That's a big deal. We need that information. Above the water with an initial velocity of 76 feet per second. And we're going to write the following equation to use that projectile motion. This is our position. Okay. And S is the position at time t. V sub naught is that initial velocity. And t is the time in seconds. And S sub naught is that initial height. Now, in these problems, this is a math class. We're not getting into the physics with friction or necessarily wind vectors coming at us. So please keep that in mind. So if we want to create a parametric situation, write this in a parametric form, since we only now have that vertical motion, we have to think about x as a constant. And y is going to be that equation of the height off the ground with respect to time to simulate that projectile. Okay? And this is in the assumption that it is in feet. Okay? So I'd like for you to fill out the following information, the table and the window. Pause the video now. So you can see this in general, how I would set up some vertical motion. So now I'm going to extend this. What if we have both, the vertical and the horizontal, and we have to think about an angle? Okay, now we're going to deal with objects not straight up. So now we're going to deal with this angle. So suppose a baseball is thrown from point y sub a ground level and initial velocity. So we're going to represent the velocity by this vector. So if theta, and this is my velocity vector, then velocity v sub naught cosine theta, comma v sub naught sine theta. The path of the ball can be modeled by the parametric equations x equals p sub naught t cosine theta, and y, we still need to think about that projectile motion, so negative 16t squared plus v sub naught t sine theta plus y sub naught. Some books will say s sub naught, so essentially that initial position. The x component, actually what I'm going to do is I'm going to take a moment and pause the video and fill out these spaces, so read through them. Okay, now you can see what everything is representing, what the x component, the effective gravity, the effective initial velocity, and the effective initial height. If you need a moment, pause the video so you can understand that information. All right, we're going to work through an entire baseball problem, and then we have a Ferris wheel problem to get through. I might need to do that on a second video. So as you can see, Brock hits a baseball 3 feet above the ground with an initial velocity of 150 feet per second and an angle of 18 degrees with the horizontal. We want to find out if the ball will clear a 20-foot fence that is 400 feet away. And so we're going to sketch a graph of the situation. We're also going to simulate the situation. We will create that wall as well for you. So take a moment and pause the video, and I would like for you to come up with the x component of the path of the ball and the y component. We'll work through the wall itself together. Information filled in that you would need to watch this path of the ball. My wall, I know that the wall is 400 feet away. There's many ways to do the height. I just want to make sure the max height is 20. I do it as 20, or whatever that height is, times a quantity 1 minus t. So it starts at 20 and then it starts going downward. We're going to watch that simulation here in a moment. So pause the video, get everything into your calculator. Okay, so I'm going to graph. We see the ball, there, the blue wall, and we see it does not clear the fence. We can look at a table of values. We can help us determine how high it is off up the wall and things like that. But we can also do this algebraic. To solve this algebraically, I'd have to take the horizontal component and set it equal to 400. And I would solve this for t using my graphing calculator. When I get that t value, when I find what this t value is, I would need to plug it in here where I'm putting a star to get that vertical distance. That is the time that the ball is 400 feet away. To get that height, we would plug it into the y and we would get that answer. We know that Brock did not hit a home run, and I'd like you to think about what you can change in order for him to hit the home run. Pause the video and create that scenario. This is how I was able to get Brock to hit the home run. We have one more problem to do, and it's going to be a you-try problem. So to check your understanding, I'd like you to do these calculator challenges. Everything on this next page. You really need to do this. You are going to be assessed at the end of the week. So please read through this, and then I will project my answers. By now, you've had time to work through the problem with Jared hitting the ball. Here are my answers. If you need time to look over it, I encourage you to take a screenshot. And here are the solutions to the last problem I have asked you to do. This wraps up 6-1 to 6-3. Take care. I'll be talking to you soon.